Okay, in this lecture, we're going to go over how you calculate the dipole moment, not just for a physical dipole, which is two opposite charges, but for any object that happens to have a net dipole moment, any funky charged object. Okay, let's just review what we talked about in the multipole expansion lecture, and that was the idea that if the total charge ended up being 0, okay, then the dipole term dominates. Okay, so what was the dipole term? Well, the dipole term of the potential said that the potential would be approximately equal to 1 over 4 pi epsilon naught divided by 1 over r, or divided by r squared, and then I would do our volume integral over the charge density, okay, times r prime, that's the length or the magnitude of the position vector for our charge. And if I was nice enough to set the coordinate system such that that r vector was aligned, okay, with the z-axis, then I can write alpha as theta. Okay, so alpha equal to theta because r is parallel to our z-axis. Okay, so that's a special orientation, but the nicest one you can do, and I need a prime on that guy. Okay, so let's write this as something a little bit different. Still have this term out front. Still have our volume integral. Okay, but instead of writing this as r prime cosine theta, I'm going to write that as the vector r prime dotted with r hat, okay, where we remember that r hat is aligned with the z-axis, okay? So when I take the dot product, that means this angle is going to be the angle between the vector or the direction of our r vector and the r prime vector. Okay, so I can rewrite that as, now that allows me to rewrite this bit as r prime dotted with r hat d tau. Okay, I'm going to write that one more time, and I'm just going to gather these terms here. And I'm going to dot that whole thing by r hat. And again, I can do that because none of these are vectors, so it doesn't matter whether how I push them around the dot product. And now I'm going to let the dipole moment be equal to the good stuff in that integral. Okay, so that stuff there. Okay, so that is the dipole moment, which we use P for. Okay, and it's still a vector because we still have a vector quantity within our integral. Okay, so let's use that. Okay, and let's go ahead and evaluate it to see what we expect. We get what we'd expect for point charges. Okay, so if I set up my problem for point charges, if you guys remember, I can have a positive charge here, Q plus, and a negative charge down here, Q minus. I can set up a coordinate system that goes between them and bisects them, and then I can define this to be the position vector for my positive charge. This would be the position vector for my negative charge, okay? So if I were to write out what the charge density of these guys is, okay, rho sub r prime. Remember, point charges, we want to, when we're doing the charge density, we need to use Dirac delta functions because there's an infinite amount of charge at an infinitely small volume right here. So I can imagine describing that with a function that is 0 except for right at this point, and that's what the Dirac delta function is. Okay, so The charge density would be equal to, in this case, we're in 3 dimensions, so the 3-dimensional Dirac delta function, and I would take r prime minus the position vector of that particular charge, like that. Okay, so this would only not be 0, okay, at this particular position here. And the other one would look similar, but I would be using the other position vector. Now when I plug that in for my integral for the dipole moment, I can split that integral up into 2 bits. And I'm actually going to cheat a little bit. I'm going to pull the q well, no, I'll just leave the q. I'm going to pull the q out of each integral though. Q, and our first integral, we're going to end up with that Dirac delta r prime minus r plus. And that's going to be evaluated at the r here, d tau, and then I'm going to get minus q, similar looking thing here. Oh, I don't know. Oof, okay. So if you remember how this worked, this just is all going to be the function here evaluated at what's subtracted here. So I'm just going to get left with my r prime plus, okay, and this will just end up being my r prime minus. And so when I write it all out, I get that the dipole moment is equal to q times the r prime plus minus q times the r prime minus. Okay, this is the same thing as doing the sum of each of those charges times their position vector. In this case, if I assume this is d over 2, okay, I would get q times the magnitude, which is d over 2 times the direction, which is z hat, in the z hat direction for the positive charge, minus q times negative d over 2 times that z hat, because this position vector is pointing in the negative z hat direction. When I add those together, I get q d z hat, okay, which is equal to our dipole moment, which is what we found before. Good. Okay, we're not crazy. Okay, but you can calculate our rho for any charge distribution. Okay, if you do that, rho will depend on all kinds of things. It'll depend on the size, the shape, and the density of the charge distribution. And sometimes you might calculate it and find that it is 0, okay, depending on how that charge is distributed. So let's do an example where we're just going to have our normal sphere here. On this sphere, we are going to have a charge distribution, rho, which looks like some constant times a Dirac delta function that's only not 0 at the radius of our shell here. Now I'll say this is a shell, not a solid sphere, times the cosine of theta. Okay, so for this kind of charge distribution, you end up getting a cosine distribution of the charge, so you get a lot more charge up here at the top, and then it falls off like a cosine, and it flips to negative when you get down here towards theta is equal to pi, and you get more negative charge. That's probably not quite right. More negative charge at the bottom, and then less as you get to the top. So you get something that looks kind of like that. Okay, and we already talked about a kind of shell that would end up with this charge distribution. Okay, so I can write the dipole moment in terms of its three components. It's a vector, so it's got components in the x, y, and z direction. Similarly, all right, our r prime vector also has components in the x, y, and z direction. And I can note that for a standard coordinate system here, spherical coordinates, this is x, y, and z. If I want to specify a particular spot here, draw some. Theta would be measured as the angle from the z-axis, and therefore z would be equal to our r prime, which is what this guy is, times the cosine of theta. Okay, try to convince yourself, if I'm thinking about doing this particular integral, it's only going to be non-zero in the pz direction. Okay, so the symmetry of the problem means that I'm not going to have any components of my dipole in the x or the y direction, and that has to do, I could do the integral here, and if you want to, you can, but if I did the integral in those particular directions, so I replace this, for example, with x and y, I would end up getting integrals that summed to 0. So we're only going to do the z direction, so it's only non-zero in z direction. Okay, so let's write out what that integral would look like. I'm just going to calculate the component of the dipole in the z direction, because that's going to be the total dipole. It's just going to be equal to the magnitude of the z component. That is going to be equal to, again, now I can replace, instead of having our r vector here, I can just have a z vector. And if I'm just looking for the magnitude, I can get rid of my vector signs here. And again, the magnitude, since it's only in the z direction, is going to be fully determined by the length of the z hat component here. Okay, writing out what all of those terms are. The charge density looked like this. And I can rewrite, no, don't want to forget that little bit. I can rewrite the z as r prime times the cosine of theta. And I'm going to put primes on these because it refers to the charge density. I'll put prime on this guy too. And I have to write out what d tau is, so I get an r prime squared times the sine of theta prime dr d theta d phi. Okay, and of course I'm going to do this integral from r to 0, from pi to 0, and from 2 pi to 0. Okay, I'm not going to do that in detail. You can do it yourself. You can stick it into Mathematica, whatever you like. Okay, but you end up getting sigma naught, the charge, that constant in the charge density formula, times r to the third minus cosine to the third theta divided by 3, and you're going to evaluate at the limits of theta, which are pi and 0. When you plug all that in, you get 2/3 sigma naught times r to the third. Okay, so you end up getting that p, the magnitude of it, is 2/3 theta naught r to the third, but you know that it is in the z hat direction, so I can go ahead and multiply that by the z hat vector to get the direction of it as well. Okay, so this is the dipole moment for a polarized sphere. Okay, and the last thing I want to know, let's go ahead and shoop. Since that was our main result here, we'll go ahead and circle that. Okay, I want to note that for this sphere, Q total is equal to 0. So the dipole term will dominate our potential. Okay, so that first term, the leading term, is going to be 0 because that, right, has Q total in it. Q total is 0. That first term is going to be 0. So our potential for the sphere, I can approximate it as being equal to that first term, which looks like the dipole moment divided by r squared plus other stuff. Since I actually know what the dipole moment is, I can write that as what I just found times z hat dotted with r hat. Okay, so magnitude gives the orientation. Because the field, it depends on how the dipole is aligned. Okay,